Hello and welcome to my advanced construction presentation on two case study examples by Al-Qarani. The following presentation will explore two examples of awe-inspiring buildings located in Istanbul, Turkey. This will include an evaluation of key features, materials and mechanisms that have been implemented within such structures in order to make them look aesthetically pleasing, as well as delivering functionality, which is a key parameter for modern projects. The first example building will explore more modern technology systems and processes, whereas the second will be focusing on a more traditional build, allowing a comparison between the two types and an understanding of how technology advances are having an impact on modern day construction. The first complex building we will look at is a Kamlika TV tower that has recently been constructed in Istanbul. This is a state-of-the-art telecommunications tower that features restaurants and observation decks and is the tallest building in the city. The building was designed by Malik Al-Tanisik architects and construction commenced in March of 2016. This took a 5-year period and construction was finally completed earlier this year in 2021. The total cost of the project was 170 million liras, which is approximately $48.5 million. Project objectives. The main objective of the TV is to provide telecommunications across the city, with 125 broadcasting transmitters being installed. This is in the hope to end visual pollution caused by scattered, outdated TV antennas that are currently seen on the rooftops in the city. As well as this main objective, the tower features a number of restaurants and observation decks with panoramic views in the hope to boost the local economy and tourism in Istanbul. The Turkish Prime Minister has stated that the tower will attract around 4.5 million visitors a year. Project brief. The main goal of the project is to benefit the city by replacing several large buildings constructed in the That leads us to the innovation of the building, which is a main reason for the building's uniqueness in construction. The principal designer stated that the tower required advanced engineering techniques, both in terms of architectural design and construction methodology. The substructure. The excavation was to a depth of 21 meters, containing multi-purpose construction levels, including the use of a car park and plant rooms. Although there is little information provided to the public on the foundation type, it can be assumed that a piled slab foundation would have been used due to the convention of similar buildings of this stature. The 21 meters deep concrete piles would have been supported by a slab which takes the load of the building uniformly, and it would have been constructed under the basement level. The image here shows a similar method of foundation construction that was used for the Shard in London. As Istanbul falls on a major earthquake zone, the building has utilized some of the state-of-the-art mitigation measures in the event of a major earthquake. As well as this, the waterproofing system for the substructure levels used reinforced concrete construction with waterproof additives, as well as a cavity wall drainage system. Superstructure of the building. The main structure of the building consists of a 203-meter concrete core, which is designed to support a 145-meter steel mast at the top of the building. This gives a total height of 369 meters. The unique facade design has been developed during wind testing stage, which also optimizes how the load of the building acts on the core. By implementing such a unique facade, it also allows inhabitable spaces to be developed inside it. Development of the facade system. The development of the facade system can be seen in the images in exploded 3D view. Here it can be seen that number 6 is the I-beam structure, which connects a concrete core to the outer shell of the building. Above this we can see the internal floor finish of the facade, where the inhabitable spaces would be. Then there is a double glazed unit, seen as number 2 on the diagram. This unit minimizes the amount of heat being let through into the building, which will reduce energy costs. Further out from this is the mullion, which is a vertical steel support column for the glass and cladding. And then finally we have number 1, which illustrates the external GRC cladding on the outer surface of the building. The glazed bay, as well as the ordinary bays, are connected to a concrete wall via a secondary steel structure. This can be seen at number 0 on the 2 diagrams, which show the facade from the internal and external view. The sheeting highlighted in blue here is a thermal insulation, which is covering the face of the concrete wall, and the facade panels utilize vertical unitized joints, as well as aluminium framing in the cladding, which prevents movement with adjacent panels and accommodates for any structural movement. Advanced construction techniques. Modern methods of construction have been utilized on the building in order to speed up the construction process. Many components were designed so that they can be assembled off-site in order to minimize installation time on-site. The adjustable brackets on the rain screen allow a direct fix to the steel frame, and the rain screens are attached to the panels before installation on the building. The rain screen themselves use innovative utilization by integrating thin glass fiber reinforced concrete, as well as the ability for this to be molded to form futuristic designs. It also benefits from reduced weight, making them easier to handle and transport, as well as being environmentally friendly. Each truss on the steel frame is individually designed and sized. This is so that the panels can have uniform behavior in terms of any vertical deflections and horizontal movements. Lower light transmitting glass has also been used on the exterior of the building to avoid glare. This is vital in acting as a cooling factor due to the climate of the city, which can often exceed temperatures of 35 degrees Celsius. The use of this glass has reduced the mean daylight factor for the bays on each floor to less than 2%. The values for each can be seen here on the figure on the right. As well as this, the shaded areas reduce solar radiation by about 38%. Although this reduces the unwanted heat inside the floors, it results in darkness, and therefore adequate lighting will be required for parts of the buildings. We will now look at a short video clip that has been captured by a drone showing the construction of the building from bottom up. This gives an idea of the scale of the building in comparison to the rest of the city. Finishes and services. Advanced technology continues to be used in the interior of the building through the finishes and services. Schindler's panoramic elevators have been chosen on both sides of the building in order to act as an element that feeds and divides the monolithic body. The elevators were designed by specialists in Switzerland and features two panoramic elevators which travel a total distance of 184 meters. This allows the visitors to experience the views of Istanbul from all angles. The image here shows the unique design of the features inside the building, as well as light fittings being fragmented into the inner skins of the envelope to provide a futuristic experience for the visitors. This has been done in an attempt to emulate the outside of the building with its similar dynamic movement. Environmental considerations and constraints. Initially, the project was created due to a successful competition in 2011 in order to prevent visual pollution across Kamlika Hill. This will replace the outdated antennas that are currently splattered across the city. There's also an environmental consideration due to the topography of the hill. High winds are often present, which is an important constraint to consider during the designing and testing stages of the building. We will now take a look at our second case study example, which is of a more traditional old structure which is equally, if not more stunning than Kamlika TV Tower. The Hagia Sophia was the largest enclosed building on Earth for nearly 1,000 years and without doubt one of the most magnificent buildings ever created. The large dome feature was a significant innovation at the time of the construction. It is often argued that there is nothing practical in the design, and it is in fact all innovation. The gold domed ceiling soars over 180 feet high and is supported by extremely strong arches. Despite being built over 1500 years ago, it is still standing, having survived multiple wars and earthquakes. The building has a rich history, having been passed from Christianity to Islam. Project brief and history. Hagia Sophia was built in 360 AD with a basilica layout and architectural features. In 405 AD, Hagia Sophia was rebuilt after it was burnt down during an uprising and was reopened in 1415. The monument today is a third Hagia Sophia built on the same ground by Justinian, who was perhaps one of the greatest rulers of the Roman Empire. The ruler initially built the structure as a cathedral in order to distract people after nearly 30,000 had died during an uprising. It is one of the greatest examples of Byzantine architecture that is still standing and features many mosaics and marble pillars that are preserved to this day. The project was completed in a period of 6 years, which is extremely quick for the medieval architects, bearing in mind that the Notre Dame Cathedral took over 100 years to complete. Islamic influence and restoration. Sultan Mehmet the Conqueror entered into the city of Constantinople after conquering it and was immediately amazed by the architecture of the structure. He then made it his mosque, which was used for over 500 years. The most famous restoration was completed in 1847 by Abdul Mesid II. He used Swiss and Italian architectures in order to help with the renovation. The domes and vaults were consolidated, columns were straightened, and decorations of the interior and exterior were altered. The structure then needed further renovation in 1999 when the rising groundwater and moisture penetration rendered brickwork unstable. Then by 2006, the dome was fully repaired and mosaics were preserved under the guidance of the World Monuments Fund. The image shows the beautiful, unique architecture of inside the structure. Superstructure. The stone floor of Hagia Sophia dates from the 6th century. After the first collapse of the vault, the broken dome was left in situ on the original floor, and a new floor was laid upon the rubble when the dome was rebuilt in the year 558. The floor is predominantly of Proconnesian marble, quarried on Marmara Island. This was the main white marble that was used in Constantinople's monuments at the time period. The main core of the building features a famous domed roof that is 31 meters in diameter. This staggeringly wide dome allows for huge open spaces inside the structure without any visible beams or columns supporting it. It has particularly spurred interest in many art historians, architects, and engineers because of the innovative way the original architects had envisioned it. The aggregate weighs 2,402 kilograms per cubic meter, which was an average weight of masonry at the time of construction. The dome rests upon four key arches that act as a support for the dome, eradicating the need for beams and columns. The arches are supported by four piers and two semi-domes. Horizontal force that is generated by the main heavy dome is suppressed by semi-domes in the east and west direction. These piers are continuously monitored to detect any movement which could possibly result in damage to the structure. And the structure is composed of stone and marble, as well as composite materials containing brick and mortar. The analytical drawing here helps to get an idea of the structure of the building, which shows the features such as the arches, piers, and semi-domes.
Ultimate replica of the church when it was consecrated in 537 AD. The original dome had a lower profile, and it collapsed after an earthquake in 558. The new dome, built in the year 562, had a much higher profile to reduce the lateral forces. This enabled the building to withstand many more earthquakes in the later centuries. The flying buttresses on the west side were built at an unknown date. Most likely, Byzantine builders came up with this solution to support the aging building. The most important Ottoman changes to the outside of the building are the minarets. The oldest minaret is the brick one at the southeast corner, built by Mehmed the Conqueror. The others were added in the 15th and 16th centuries. The original courtyard of Hagia Sophia was demolished and removed over time. When Sultan said,
We will now take a look at a short video clip which shows the changes that were made to the exterior of the building since the year 537 up to the present day. Finishes and services. The building features heavy marble doorways, such as the one in the image on the right. This is decorated in fish and fruit motifs. Such doors were used for events, for example meetings. The building also has preserved many of the old Christian mosaics which are seen in high quality artwork and results in visitors from across the world coming to Istanbul. As the building is now used as a mosque, it features the famous marble platform where the call to prayer is performed at. Environmental considerations and constraints. The biggest environmental constraint for the building would be earthquakes. This is because Istanbul is situated on a fault zone, so it's susceptible to many earthquakes. The earthquakes can cause the arches to have excessive movement, which would result in the collapse of the dome and the superstructure. Water moisture can also be an issue, as it can seep into the building and damage it. The structure must be continuously monitored for movement in the supporting arches and buttresses in order to prevent collapse of a heavy dome. And conservationists are also concerned over the amount of play in the complex structure. Therefore, extensive maintenance is required for peeling walls and ceilings, discolor and stains that are caused by water seepage. Comparison between the two building types. Both structures are very innovative but in different ways. The Kamlika Tower has utilized modern technology systems in order to build a futuristic design that also provides functionality, whereas the Hagia Sophia, which also fits its purpose of a place of worship, has relied on a complex yet beautiful architecture to provide its innovation, especially considering the age that it was constructed in. The building standards would obviously differ between the structures given the time period that they have been constructed in. There would have been little consideration for regulations at the time of the construction of Hagia Sophia, whereas Kamlika Tower would have been built on masses of regulations, for example, earthquake resistant and insulation regulations. Also, the materials used for the construction of Kamlika Tower is mainly concrete and steel, whereas Hagia Sophia used more common materials that were in the olden times, such as masonry, stone, and marble. These materials are obviously much heavier and therefore provide a greater stress on the supporting structures of buildings. Hagia Sophia shows that innovation has been created throughout the history of architecture, despite little knowledge and technologies at the time. However, it is clear that as technology advances, innovation becomes more reliable and enhanced in terms of productivity and sustainability of a building. Thank you for listening to my presentation. The references for the images and information are on the following slides.